potential energy. It's thermochemistry. Oh, it's a study in heat. Heat is all that heat is. Systems and surroundings all around.
Alright, so we're going to pick up where we left off in the last video about Chapter 6 and how there are different ways to calculate enthalpy. Remember, enthalpy is delta H, and we said one of the ways that we can calculate enthalpy is by calorimetry. And so calorimetry, we said, is usually done at a constant pressure, and so what we're looking at is heat under a constant pressure. There is another way to do calorimetry. So this is known as coffee cup calorimetry. This is what we'll be doing in lab. This is what's commonly done to calculate delta H. We can also calculate delta H through a bomb calorimeter. And we mentioned that in class on how that's how they used to calculate the energy within your food. And so a bomb calorimeter is done at a constant volume. And so it's slightly different. We're not going to really worry about the math associated with a bomb calorimeter because there's enough math to worry about the coffee cup calorimeter or at constant pressure. So that's the first way we can calculate enthalpy. Number one, we can do it in the lab through calorimetry. Number two, we can do what's known as Hess's law. So, Hess's law states that if we want to find the enthalpy of a reaction, so we're going to look at number 82 for an example of this. If you want to find enthalpy of a reaction, you are able to take known enthalpies of other reactions and combine them together to find the enthalpy of the reaction you're looking for. So let's look at an example, and I'll walk through what that actually means as we do this. So methane gas plus chlorine gas makes carbon tetrachloride. Had an extra C in there. Gas plus hydrochloric gas. And so we want to know the delta H reaction of this, but it's really hard to sometimes go into the lab to do this type of experiment, to calculate the energy change, to work on a variety of different things, and so there has to be a different way to do it. So this is my favorite way of calculating delta H because it's a big puzzle. To me, it's a big puzzle. So you will be given, if you are asked to calculate delta H this way, you will be given a variety of different equations. So let's make methane. And we know the delta H of this reaction is negative 74.6 kilojoules. And what I want you to do is every time you see a sign, I want you to start thinking, is this an exothermic or an endothermic reaction? Since we see a negative delta H here, circle that, this would be an exothermic reaction. This reaction gives off energy or heat. Here's another one. Carbon plus chlorine gas makes carbon tetrachloride. And the delta H of this reaction is negative 95.7 kilojoules. And then I'm going to give you one more. H2 gas plus Cl2 gas goes to 2 HCl gas. And we know the delta H of this reaction is equal to negative 92.3 kilojoules. Now, Hess's law states that we are able to manipulate one of these three equations, or all three equations, or two of the three, to try to get things to match this equation. And so what we're going to see is we can flip equations, so we can turn products make them reactants, make reactants products. If we were to do that manipulation, if we were to flip an equation, then we have to change the sign of the delta H. We can also multiply these equations, right? So we need a balanced equation. So you can see we have a 4 here and a 4 here. Let's say one of the equations had an 8 in front of the HCl. If that's the case, then you would multiply by 1/2. Whenever you multiply your equations by 1/2, you also have to multiply the delta H by the exact same factor. So let's take a look at what we're going to do. So the first thing we need to do is to make sure all of the reactants in the reaction we're trying to find, which is this one. So this is our guidepost. We want to make sure all of our reactants on the reactant side, all our products on the product side of equations 1 through 3. So what I'm going to do, if you've noticed, we need methane or CH4 on the left, on the reactant side. So equation number 1 contains methane, but it's on the product side. So let's go ahead and do this in a different color to show you that we've switched it. So we're going to flip it. So we're going to make CH4 gas go to 2H2 gas plus carbon solid. Now remember, if we flip an equation, then we have to change the sign of the delta H. So the delta H of 2H2 plus C plus carbon solid going to methane, that equals negative 74.6. But since we reversed the equation, we now have to change the sign of the delta H. So let's look at the second equation. We're looking for carbon tetrachloride and some Cl2s. Some chlorine gas on the reactant side. If we look at equation number 2 looks good. Both the reactants and products are on the same side where we want them. Now let's look at the last one. So we need chlorine gas on the left, or on the reactant side, check, and we need hydrochloric acid on the right, check. Now there's an issue. The issue comes in with these 4s. So I don't see a 4 in number 3. But I do see a 2 right there. So how do we go from 2 to 4? I'm going to multiply everything by 2. And that is how everything will change. Now I know what you're thinking. Dr. Bishop, there's a 4 in front of the Cl2. Just bear with me just 1 second. And I'll show you why this is what needs to be done. So if we multiply everything by 2, then we need to multiply the delta H by 2. It keeps the same sign because we did not flip it, but it'll be minus 184.60 kilojoules. Now, what we're going to do, and what Hess's law allows us to do, is we are allowed to add these equations together. Whatever you see on the reactant side and whatever you see on the product side, if they match, just like with a net ionic equation, you can cross them off. So there's a carbon solid, we can cross that off. There's 2 hydrogen gases. With 2 hydrogen gases, we cross those off. You have to make sure that the number of moles of the molecules are the same. So we can cross off hydrogen gas because we have 2 and 2. 2 on the reactants, 2 on the products. So now when we add those together, we get CH4 plus, we have 2 Cl2s plus 2 Cl2s, and that's 4 Cl2s. Going to carbon tetrachloride, oops, forgot the 4, plus 4 HCl. Now, does this resemble that? Absolutely, it's the same exact thing. And so that's what we're looking for. And so what we can do is we can then say delta H of this reaction is us adding up all of the delta H's, and what we get is minus 205.7 kilojoules. And so that is another way to calculate enthalpy when we can't really do it in the lab. So, for practice on this, because it will take some practice to realize what we have to do. So to practice this, I want you guys to do number 79 and number 80, and I want you to turn that in on Friday, October the 12th. So that way you'll have a little bit of time to go over this. If you have any questions, please come see me. I apologize, I'm erasing this very slowly, but I want to keep up the same slide and the same notes on top, because we're going to do one more way. So there's 3 ways we can calculate delta H. The first way is to go into the lab to calculate it using a calorimeter. The second way is through Hess's law. The third way is using standard states. And so standard states are where these states of matter are most stable. Usually if you're talking about a liquid or an aqueous solution, it's at 1 molar. Everything is at 1 atmosphere, at 1 mole. And so it's usually, this is what we mean by standard states. It's the most stable state that things can form. We'll talk a little bit more about it in class. But let's say I'm giving you this equation. So N2H4 liquid plus H2O gas going to 2 dinitrogen monoxide or nitrous oxide gas plus more gas. And actually, if I could read my own handwriting, this is number 85 in your book, and it's N2O4 gas. It makes no sense on why you would put H2O gas in the reactants and get H2O gas in the products. So you have N2H4 plus N2O4 gives you N2O plus H2O. This is a balanced equation. We need a balanced equation for this. The other thing that's very important when using standard states are those right there. The states of matter will be very, very important when looking at these standard states. So, when we talk about standard states, we put a little knot. That's what that little circle means. It's a little knot on this. So delta H naught of the reaction tells us that we're doing standard states. Now, let's think about this. Delta means it's a state function. So it's going to be final minus initial. So we're going to have E, the sum of the delta H of formation of the products, minus the sum of the delta H of the reactants. Right, so final minus initial. But since we have more than one, we have to take the sum of those. So what does this look like? So it would look like the products. We have N2O gas plus H2O gas minus N2H4 liquid plus N2O4 gas. Right? And so what we also have to pay attention to are the number of moles of each compound, because that will change how much energy we have for the different reactants or products. And so what you would do, how you would solve this problem is you would be given the standard states of formation, or the delta H of formation, of these different compounds. You would be given them. And so there's a table in your book that you can look at that will help you with these. And this is why states of matter are important. Because if you don't have the correct state of matter, then you cannot get the correct standard or delta H of formation. So, if we go to the book, we find that it being 81.6 plus negative 241.8. Remember, keep the signs. The signs are very important. And so N2H4 was 95.4 plus 9.16. And then all we have to do is just do the multiplication and addition. And when we do that, we get a minus 320.4 minus 104.56. When we do that, we can then calculate delta H not of the reaction as being negative 424.96 kilojoule. This one's in kilojoules. It's a really bad kilojoules. Kilojoules per mole. And so that's the standard states. We can use standard states of formation. We'll talk a little bit about standard states in class. But those are the three main ways that we calculate enthalpy. In the lab, through calorimetry, using Hess's law, where we can take a bunch of smaller reactions, add them together, or we can use the standard states of formation. I really hope this helps.